USeen podcast.
Type 2 diabetes is an accelerating global crisis. Catching it early is absolutely vital to prevent severe, long-term consequences, like cardiovascular disease and kidney failure. To assist with early diagnosis, modern medicine generates a massive amount of digital records. With thousands of data points per patient, you might expect artificial intelligence to step in and make perfect medical predictions. But real-world clinical data is incredibly complex. In practice, it's high-dimensional, highly unpredictable, and full of unexpected errors. This table illustrates exactly where these errors hide. Look at the continuous numeric predictor variables, like insulin or skin thickness. These specific measurements are highly susceptible to extreme outlier readings, invalid zeros, and natural biological variability. If you blindly feed this contaminated medical data directly into an artificial intelligence model, the algorithm gets confused. It learns the noise instead of the disease, rendering its predictions dangerously unreliable for patient care. Data scientists typically attempt to clean up this complexity using a traditional tool called principal component analysis, or PCA. At its baseline, standard PCA simplifies datasets by grouping correlated variables together. It removes redundancy to make massive clinical spreadsheets more manageable for the algorithm. However, standard PCA has a fatal flaw. It is incredibly sensitive to outliers. Because of how it calculates variance, a few extreme measurement errors can bias the entire equation. If you plot a cluster of normal patient records, the calculation finds the center. But the moment you introduce a few extreme outliers, the entire axis is violently pulled off-center, completely misrepresenting the patient's actual clinical state. Simply shrinking the data down does not work if you bake the errors directly into the final model. True diagnostic AI requires a mathematical system built to withstand extreme anomalies without losing the underlying biological truth. To bypass this limitation, researchers implemented an upgraded algorithm built specifically for contaminated biomedical data, robust principal component analysis, or RPCA. RPCA mathematically splits the observed data matrix X into two distinct parts. The first component, L, the low-rank matrix, captures the true systematic structure of the disease. The second component, S, the sparse matrix, acts as a trap to catch all corrupted observations and extreme outliers. By physically walling off the noise into its own matrix, RPCA delivers a perfectly clean dataset, resolving the primary bottleneck in medical machine learning. With the noise filtered out, the newly cleaned data moves to the next phase, an ensemble learning model that will actually diagnose the patient. The researchers utilized extremely randomized trees, or ERT, as their decision-making model. ERT aggregates multiple algorithmic decision paths, checking hundreds of different routes to reduce variance. ERT is unique because it forces intense randomness into how it splits data at every node. This constant extreme randomization makes the final decision highly resistant to any residual noise. To stress test the pipeline, researchers generated two overlapping data clusters, simulating a hard-to-detect disease, then bombarded them with randomized outliers reaching 40% contamination. Standard PCA failed completely, its boundary line wildly oscillating, dropping accuracy to near random guessing. This simulation proves a stark reality. Advanced AI decision engines are completely useless if the initial data processing cannot survive heavy real-world contamination. Following the simulation, the researchers tested their combined model on empirical evidence using the real-world Pima Indians diabetes clinical dataset. Looking at these evaluation formulas, the researchers focused heavily on a strict metric, sensitivity. While accuracy matters, sensitivity calculates true positives against false negatives, measuring the model's precise ability to correctly catch actual positive diabetes cases. The final empirical results are clear. The optimized RPCA-ERT model achieved an accuracy of 0.8954 and a highly impressive sensitivity of 0.9434, easily outperforming the baseline methods. By pairing a mathematical noise filter directly with a highly randomized decision engine, the researchers created a diagnostic tool truly viable for clinical environments. For hospitals, the implication is incredibly practical. Machine learning is finally equipped to handle the messy, error-prone realities of everyday electronic health records. Reaching over 94% sensitivity means drastically fewer misdiagnoses. Catching the disease accurately and early directly prevents severe patient consequences down the line. This study underscores an essential law of data science. The raw processing power of the algorithm is entirely dependent on the quality of the data preparation happening right behind it. To advance medical AI, algorithms don't need to simply think faster. They need to see the patient clearly by ignoring the noise.